Impulse and momentum. Impulse and momentum is a different way of looking at forces combined with kinematics, and I'll show you the derivation in just a little bit. But first, let's start with a couple of definitions. The impulse of a force is the product of the average force and the time interval during which the force acts. So it's I is equal to force F delta T, or Ft, depending on how you want to look at it. Linear momentum is the product of the object's mass and the velocity. The symbol for momentum is P, and then we have mass and velocity. Now, what's important in this case is that these are both vectors, so that's why the linear momentum is important, because it's in a specific axis that you have to be concerned with. All right, so let me show you the quick derivation. Let's put this in a different color. All right, Newton's second law, F is equal to ma. In acceleration, the basic definition we have is A is equal to delta V over delta T. And we can think of this as Vf minus V naught over the change in time. And so, if you look at this equation, we have F equals ma, and we have A is equal to this. All we're going to do is plug this into this equation over here. And we can plug it in one of two ways. So let's go and do this way. F is equal to m times delta V over delta T. And so, if we start to work this out, we can move this over to the other side. So we have force times the change in time, which should look familiar at this point. That's impulse, is equal to the mass times the change in velocity. And that should look very familiar to you as well. That's momentum. This is impulse. And so we can delve a little bit deeper into this and work with it in this format, Vf minus V naught. And so we get force delta T is equal to the mass times the final velocity minus the initial velocity. And if we distribute this, this becomes force delta T is equal to mVf minus mv naught. And this is the most detailed equation that we have for impulse and momentum. But you could use any of these equations, or versions of the equations, or forms of the equation when working out your problems. So let's do a quick practice. A baseball with a mass of 0.14 kilograms has an initial velocity of negative 38 meters per second as it approaches a bat. The ball departs the bat with a final velocity of 58 meters per second. The time of contact is 1.6 times 10 to the negative third seconds. Find the average net force exerted on the ball by the bat. And so if we look at all of our variables that are given to us, we can start listing these out. So we have a mass of 0.14 kilograms. We have an initial velocity of negative 38 meters per second. We have a final velocity of 58 meters per second. We have a time, or change in time, think of it like that, as 1.6 times 10 to the negative third seconds. And we are asked to find the force. So all we have to do now is, since we've labeled all of our variables, just plug it into our equation. So we're looking for the force times 1, put this in parentheses, 1.6 times 10 to the negative third. That's going to be equal to the mass, 0.14, times 58 minus 0.14 times negative 38. And when you start working this out, you should get force times 1.6 times 10 to the negative third is equal to, when you work out that math, you should get 13.44. And then divide that, and you should get a force of 8,400 newtons. And there we go. That's using the force, time, mass, velocity, the impulse and momentum theory. So, conservation of linear momentum. So now we know what momentum is. Momentum is the mass times velocity. The total linear momentum of an isolated system remains constant. An isolated system is one for which the vector sum of the external forces acting on the system is 0. So we define the isolated system And what you should see here in this particular example, we have a collision and we have a truck that's moving and a car that's not. And so if we were to measure the momentum of this system, initially it would just be of the truck, and that would be the total momentum down here, 60,000. Now after they collide, the truck itself loses momentum, but it's given to the car. And so in this case, the momentum in total is still 60,000, even though the velocities have changed in the system. So mvf is equal to mv naught. Final momentum is equal to initial momentum. Now, there are two main types of collisions. We have a fully elastic and we have fully inelastic. So in fully elastic, this is one in which the total kinetic energy of the system after the collision is equal to the total kinetic energy before the collision, which basically means not only is momentum conserved, but so is energy. For a fully inelastic collision, this is one in which the total kinetic energy of the system is not the same before and after the collision, and typically this is if the objects stick together after colliding, the collision is said to be completely inelastic. Now, in real life, there will be nothing that is fully elastic or fully inelastic. It will typically be a combination of the two. But for our calculations, it's going to be much easier if we say something is 100% elastic or something is 100% inelastic. And so that'll be for our calculations. For your equations, this is what it looks like. If we have a fully elastic collision, we have two equations we can work with. Now these look long and complicated, but if you look carefully at these, you should be able to see some common themes. So for example, mv, that's momentum. So this is momentum final of the first mass and the second mass, and the initial momentum of both masses. And that's all that this is saying here. For the kinetic energy, we should see that it's 1/2 mv squared, and that's all that this is a repetition of, whereas this is the final of the first mass, final of the second mass, initial of the first, initial of the second. For fully inelastic collisions, though, we only have momentum that is conserved, and so this is typically what it will look like if we have two objects. So we have m1 v01 plus m2 v02, that's the initial momentum. And the reason why the final momentum has the two masses added together is because since they stick together, their final velocity will be the same. And so we can simplify this so it looks like this, m1 plus m2 in parentheses times the final velocity. So here are the questions I want to leave you off with. What is crucial to understanding impulse momentum? And what are the similarities between impulse momentum and work and energy? And then once you do that, see if you can solve this problem.